question here was to calculate the percent by mass of carbon in C6H12O6, which, by the way, anybody know what that is? Here's the glucose. Yeah, it's glucose. Glucose. So, percentage of carbon in glucose is 40.00%. If you came up with 39.99, that would be accepted. And it looks like we're in pretty darn good shape. Somebody maybe either entered it wrong or just calculated the molar mass or counted hydrogens wrong or something. But it looks like collectively in the class, and this person forgot to do what? Multiply by 100. Okay? So, well, today we're moving on to Chapter 7, and it's kind of interesting. I was talking to a student that's taking a high school chemistry class last night, and they're like in Chapter 3, just starting dimensional analysis, and they can't believe how fast we're going and everything. But, I mean, this is the pace. We're covering this in one semester. And when I was a student, this was probably the stuff that turned me on to chemistry. I was a math major and music major before I started college, and got into a chemistry class accidentally and got into the chemical reactions, and this is really what turned me on to chemistry. So what we're going to start with here today, though, is a demonstration, one that you saw on day 1 in here, but we're now going to put it in a new context. And of course, it means we got to light some balloons off, which is always fun. So we're going to start with the first one down here in red. And if you start, oh, we should probably turn the lights down just a little bit. A little more fun with the, yeah, we can kind of leave it like that. Maybe dim it, just dim it for the mood. There we go. So we'll come over here, and if you startle easily, once again, you might want to cover your ears or your eyes or both. Okay, so anybody remember what's in that one?
Helium.
Helium, right. And then we go to this next one right here. Again, if you startle easily, you might want to cover your ears. Wow, that was fun. Okay. That one there would have been hydrogen. And then we got to go down to the last one here. This is one that I need my ear protection for. I think we might have done this day 1 also. Sometimes I skip this day 1 because we like to save the suspense. But I'm going to put my ear protection on. You will need to put your ear protection on as well, which is like your fingers in your ears type of thing. And I can't do this one unless you do cover your ears. So if you could, cover your ears, please. All right. And that one contained? Well, it contained hydrogen and oxygen. So what we're going to do here is we're going to write out a chemical equation for what we just observed. In fact, the difference between the last two is each one of these last two was a reaction of hydrogen with oxygen. This is a hydrogen with oxygen reaction. This one was a hydrogen with hydrogen with oxygen reaction. The difference is that this one here just contained hydrogen. So in order for the hydrogen to react with the oxygen, the balloon first had to explode. It had to pop first. And once it exploded, then it mixed with the oxygen in the air. This one over here, I went to the tank of oxygen that we have stored there, and I put pure oxygen in there with the hydrogen. And I made a special combination, put them in there, of 2 volumes of hydrogen for every 1 volume of oxygen. And of course, if I take 2 volumes of hydrogen, combine it with 1 volume of oxygen and cause them to react, what do I wind up forming? H2O. So we're going to write out a chemical equation that shows what just happened. And we're going to start first with words. And we'll put it in words like this. We say that hydrogen gas reacts with oxygen gas to produce, and what did we say we produced again? H2O, which we call water. And in what phase do you think we produced the water over here? Produced as a gas. So we didn't get splashed with water here in the front row or anything. So we got water here in the gaseous phase. Now, what is another name for water in the gaseous phase? Water in the gaseous phase. If you heat water up, what does it form? Steam. So we call steam water in the gaseous phase, or we call water in the gaseous phase steam. So now we want to write this out as a chemical equation. We need to remember what the formula is for hydrogen gas. What is the formula for hydrogen gas? H2, good. And the formula for oxygen is? O2. And the formula for water is? H2O. And then we put phase labels after each one of the chemical formulas to indicate the phase that is present. And of course, G would stand for gas. If we want to show a liquid, we'd put L. If we want to show solid, we'd put S. And there's one other phase we've seen thus far in here, and that is aqueous, which we label as AQ. Right. And aqueous means dissolved in water. So these are what we call phase labels, and phase labels are placed after the chemical formulas in a chemical equation. This here is a chemical equation. So now if we were to go ahead and show what happened here, I'm going to set my stuff aside a bit and see if we have, takes a while, oh great, focus works today. So we'll come over here to my molecular model kit, and I'm going to make a quick model of hydrogen. This here is the H2. We use the white spheres, or the white balls in here, to represent hydrogen, and we use the red ones to represent oxygen. So again, the formula for hydrogen is H2. The formula for oxygen is O2. So if we look at this chemical equation, what happens when a reaction takes place is that molecules collide with each other. When they collide, some bonds break and other bonds reform. And so I take these pieces apart here and reassemble them. We wind up now with our molecule of H2O, but it turns out that we're showing also some spare parts. And the spare parts were not a part of our original chemical equation. So what I'm going to do is I'm going to put these models back together and make my hydrogen and oxygen. So put the hydrogen back here. And what I'm going to do now is I'm going to come back to my kit, and I'm going to take another hydrogen molecule. And so now I have two hydrogen molecules that are up here. So what I do is I come back to my chemical equation, and because I'm showing two hydrogen molecules, I am going to write, hurry up here, I hate this thing, there we go. Because we're starting with two hydrogen molecules, I am going to write a 2 out front here in front of the H2 to indicate the fact that I have two hydrogen molecules. Now the reason for that again is because that first time I had spare parts that were showing up out here that was not showing up in our chemical equation. So now we have a reaction occurring, molecules collide with each other, and what happens is that some bonds break and other bonds reform. And as we put them together, we wind up with one water molecule, and now we wind up with two water molecules. And how many spare parts do we have? None. And so this is really demonstrates what we learned and actually how the law of conservation of matter came about. That was one of the first things we learned about in here was the law of conservation of matter, the law of conservation of mass. And in there we said we can neither create matter nor destroy matter as a result of a chemical reaction. And once again, we didn't create anything, didn't destroy anything. We have the same number of parts here at the end as we had at the beginning. And of course, those parts represent atoms. So if we come back here then to the chemical equation, and we want to correctly reflect this, what do we need to do to the equation? Put a 2 in front of the H2O, exactly. So we put a 2 right here, and we put the 2 in front of here now. This is what we call a balanced chemical equation. This is a balanced chemical equation. And a balanced chemical equation is one that conforms to the law of conservation of matter. Which is what they must do in the real world. Because, again, we can neither create matter nor destroy matter as a result of a chemical reaction. Now, we may have also mentioned this when we were going through chemical change and physical change, but a chemical reaction and a chemical change are the same thing. So if we use the term chemical change before, what we really meant is a chemical reaction had taken place. Now, some terminology. These numbers that I'm showing out front here, anybody know what these are called? These are called coefficients. Exactly, these are called coefficients. Now, where else have you heard of coefficients before? In math, right? In algebra. And what does a coefficient mean we need to do? Multiply. All right. So if we looked at something like 2xy, the coefficient in this case is a 2, and this means we take 2 times x times y. And so coefficients work the same way here. If we want to know the number of hydrogens that are in here, we take 2 times 2, which means there's a total of 4 hydrogen atoms. If we want to know the number of hydrogens over here, we take 2 times 2, we get 4 hydrogen atoms here. Now, there is a coefficient for the oxygen. And what is that coefficient? 1, right. We don't write a coefficient of 1 because 1s are generally implied. Okay, just like we don't write H2O1, we know that there's 1 oxygen there because it's implied. The same thing here, we don't write a 1 in front of here to indicate what the coefficient is, unless, for example, now we are in mastering chemistry where it's actually looking for you to input something. It's looking for you to input, and it says, what are the coefficients in this balanced chemical equation? You would say they are 2, 1, and 2. So again, if we were asked what the coefficients are, they are 2, 1, and 2. It's not 2, 0, and 2, because of course if this was 0, 0 times any number is 0. And so there has to be something there. And when we don't write it in, the number that's implied is the number 1. The values are the substances we see on the left-hand side of the arrow. These here we refer to as the reactants. And on the right-hand side of the arrow, we refer to these as products. And you shouldn't ever get reactants and products mixed up, because if you worked in a factory or something, you make a product, right? You make a product. Product is what you get at the end. It's not what you start with, it's what you end with. So the products are what we end with, the reactants are what we start with. Chemical equation can have 1 or more reactants. In this case, we're showing 2 reactants, and it can have 1 or more product. In this case, we're showing a single product, that product being H2O. So, any questions on this one here? All right, let's look at another one. Again, we're going to look at this in a new context because now we've seen some chemistry already in here, and we talked about chemical change in the past, so now let's actually write out what's happening. And this here is some magnesium, and I believe we've seen the magnesium in here before. We've got a nice shiny metal strip. There we go. Nice shiny metal strip. And what I'm going to do now is I'm going to ignite this magnesium. And we'll watch what happens when we do so. Again, this is probably a little more fun if we turn the lights down. We'll turn this down here as well. Now this is one that you do not want to look at directly because it is rather bright, so if you look at it, just kind of look a little bit off to the side of the magnesium. There we go. And we see that this one here is burning very brightly. Well, it's taking its sweet old time. There we go. We'll put that in. And now if we look at the product that is produced, we see we wind up with a white powder that's different than the metal. We have a small piece of metal that's left in here, but then we have the white powder that was produced. So now I'd like to write out a chemical equation for what just happened. So let's first of all put it into words. Starting with words. We started with magnesium in which phase? Solid. So we'd say that solid magnesium. Start with solid magnesium. We're going to have to get a new box here, I think. So solid magnesium reacts with. What do you suppose it reacts with? Oxygen. Good. Whenever you see something burn, you should always assume that what it's reacting with is the oxygen in the air. So solid magnesium reacts with oxygen gas. And you can't say it reacts with fire, because if I asked you what is the chemical composition of fire, you would say, I don't know. Okay? Because you don't know. Fire is actually the heat energy that's being given off when it does react, when something does react. So solid magnesium reacts with oxygen gas. And what do you think we produced? Well, think about this. How many elements do we have here? 2. So we put those 2 together, and what are we going to get? Magnesium oxide. Magnesium oxide. So again, solid magnesium reacts with oxygen gas to produce magnesium oxide. And what phase is that magnesium oxide in? This here's a solid, right? So we could say it reacted to produce solid magnesium hydroxide, or we could put solid at the end, magnesium hydroxide, solid. And then, from here we go ahead and write out a chemical equation. What is the formula for magnesium? Mg. What is the formula? Oh, and the phase label? S. We reacted with oxygen, which is O2. Now, by the way, why do we put simply Mg here with no subscript, but we put a subscript after the oxygen? It's not a Hankel-Griff, right? And what does Hankel-Griff tell us? Diatomic elements, right? So oxygen is one of our diatomic elements. In case you've forgotten those We have 7 diatomic elements. Those are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Those are your 7 diatomic elements. And when we write them as pure substances in chemical equations, we write them coming in pairs. Diatomic means they contain 2 atoms. So then they produced magnesium oxide. Formula for magnesium oxide is MgO. What is it? Is it Mg or MgO2? Well, now this is where we can't forget what we already learned, and this is where people start taking a detour. Okay, they go the wrong direction with these because you had to know your nomenclature. That's why we covered nomenclature first, was for us to figure out what these formulas are. So if we go to our periodic tables, let's pull those out. Anybody need a new periodic table? Once again, you can never have too many. Anybody need one? Never have too many periodic tables. All right. So let's go ahead and figure out what the charge is on the magnesium. Magnesium would be Mg with the charge of 2 plus. Oxygen is O with the charge of 2 negative. So if we have Mg with the 2 plus and O with the charge of 2 minus, the formula is MgO. And then the phase label we put on here is solid, or S. So this is our chemical equation. Now at this point we inspect the chemical equation. We ask ourselves, is this balanced to the law of conservation of matter? Is the number of magnesiums the same on each side? No. What is it? Yeah, it is. How about oxygen? No, it's not. So now if we want to balance the oxygens, what do we need to do? Yeah, we're going to multiply everything by 2. We put a number out front called a coefficient. We do not balance with subscripts, because if we had put a 2 down here, we are now creating the formula of something that doesn't exist. Okay? Because the formula for magnesium oxide is MgO. The way we balance is to use coefficients. When we use coefficients, coefficients always go where? In the front. They don't go in the middle. You didn't learn in algebra to write it as x to y. You write it as 2xy by putting that coefficient out the front. The chemical formulas are the same way. We put the coefficient out at the front. And when we do that, then this tells us we have 2 of the magnesium hydroxides. So because we now have 2 magnesiums, we come back to this side and we put a 2 here in front of the Mg. And this gives us a balanced chemical equation. Okay, next up, let's try this one here. Nitrogen gas reacts with oxygen gas. So nitrogen gas reacts with oxygen gas. No, let's not do oxygen. Let's do nitrogen. What do I want to do this time? Hydrogen. There we go. Hydrogen gas. Maybe that's what I said the first time. I've been awake like since 3 o'clock, so I'm kind of wired right now. To produce ammonia in the gaseous phase. So now to write out a chemical equation for this, we start by writing a formula for nitrogen gas. Formula for nitrogen would be N2. And we put a subscript of 2 because nitrogen is one of our diatomic elements. Phase label we put is G for gas. Reacts with hydrogen gas. Hydrogen would be H2. Phase label would be gas. And this produces NH3. Now I forget if we've talked about, yeah, I think we just did this one the other day, right? You need to know from this point forward the formula for ammonia. Ammonia would be NH3. The phase label is G. So now to balance it, we have some strategies for balancing chemical equations. And these I had laying out here when you came in today. Anybody not hand out? Okay. Breach. We can then look at the strategies for balancing chemical equations. And again, these are strategies, these aren't rules. And one of the strategies here, first of all, says when it comes to balancing a chemical equation, we balance the simplest formula or element last. So as we look at this, it's really kind of hard to say which one is the simplest. We only see one nitrogen over here, two nitrogens here, so maybe nitrogen is the simplest of them, so we maybe leave this one to last. There'll be others where it's probably more apparent which one is the simplest. The next strategy, number 2, is to use least common multiples between two numbers. So if we look at hydrogen, we see two hydrogens over here. We see how many over here? 3. Least common multiple between 2 and 3 is 6. So if we want to make 6 oxygens on the left, what number do we need in front of the H2? And then in front of the NH3 we'd put 2. So again, that gives us 6 hydrogens here, matches the 6 here. Then we go to the simple one, which was the nitrogen, and you see simply by using the least common multiple, we already got that figured out. Just how many nitrogens are there here? 2. How many are there here? 2. This is a balanced chemical equation. Now sometimes what some of you may prefer to do is to make a table of sorts. And when you make your table, I would construct it something like this. I'm going to move these up just a bit here. Would make a table where I'd put the reactants on one side, and I'd put the products on the other side, and then I just label the elements in there. I have, again, the reactants here on the left, products on the right, and then the two elements in this case are nitrogen and hydrogen. So one way to do it then is just by tallying them up. You might start by looking at these, showing 2 nitrogens and 2 hydrogens on the left, 1 nitrogen and 3 hydrogens on the right. And basically your goal is to make sure your number of tallies here for each element is the same for each of these rows. So if we see that nitrogen now isn't balanced, we have 2 and 1 here, we might go ahead and balance this by putting a 2 in front of the NH3. Of course, by putting the 2 in front of the NH3, we now wind up with how many nitrogens here? 2. And how many hydrogens? 6, right? So we put in 1, 2, 3, 4, 5, 6. It looks like our nitrogens are now balanced. We want to come back and balance the hydrogens. What do we need to put in front of the H2? 3. We put that in there. That then changes it, so we have a total of 6 here on the left. So this is another way you can keep track of them, is just to tally them up and to make sure that the reactant and product side have the same number of atoms on each side. So again, there's no hard and fast rule about the method of balancing. However, if you generally follow these strategies here, your chances of success are a lot better. So any questions on these? Any questions on these here? So let's try these for practice. And these 3 will come up right in a row on the Socrative app. But let's try to get them all balanced first. So let's balance these equations. We will have vanadium reacting with oxygen to yield V2O5. And by the way, we do not always need to include phase labels. Sometimes we need them for the context of the reaction. Next one, we'll have aluminum reacting with O2 to yield aluminum oxide. And then the last one, we'll have potassium chlorate decomposing to yield potassium chloride plus oxygen gas. So take a couple minutes here to balance these. 3, 2, 1. Correct answer is 5. Correct answer is 5. And so in doing this one, if you follow your strategies, which one of these should you be leaving to last? Probably the V. This is the simplest. So if we leave V to last, that means we should balance the oxygen. So we see there's 2 here and 5 here. Least common multiple of 5 and 2 is 10. So how do we make 10 oxygens here? And to make 10 on the other side, put a 2. Once we put that in front of there, then we need to balance the V's by putting a 4 out front. Good. Next up, balance of the smallest whole number coefficients. Read these carefully, because these are how they are asked in multiple choice questions. When balance of the smallest whole number coefficients, the sum of the coefficients is. Remember, if you don't write a coefficient, the coefficient that is implied is the number 1. We'll sum them together. And once we get these here, we'll give you about 15 seconds. And we're going to count down. 5, 4, 3, 2, 1. Correct answer is 9. Very good. And it's 9 because the coefficient on aluminum is 4. For oxygen it is 3. And for the aluminum oxide it is 2. 4, 3, and 2 sum to give us 9. And then the last one. When balanced with the smallest whole number coefficients, the coefficient of KCl is. Now notice that it's emphasized, we're looking for the smallest. If you can reduce your coefficients down, you always want to reduce them down. So we count down on this one. 5, 4, 3, 2, 1. And the correct answer is 2. Very good. And so the coefficients left to right are 2, 2, and 3. Any questions on these? Any questions? All right. Now, just as a quick reminder, if you've not been looking on the D2L in the lecture class, should you miss class or you want to review stuff, where can you find all of your class lectures? Content. So you go to Materials, Content. And if you were to look, for example, at the 26th, you're going to find our notes as well as a video here that explains how we did things. So again, all the notes we take and everything are uploaded to D2L. And then I have some videos, some caption videos that I've added onto that content section that go through some of the same concepts. Today on the 28th, if you were to look there, you're going to find strategies for balancing chemical equations, and you're going to find some explanations videos that goes through these. But again, you're going to find these strategies listed on there. So next one I'm going to do is this one. And I'm going to take some hydrogen peroxide. And I'm going to put some hydrogen peroxide into this, what is it, a Coke bottle. I'm really careful so I don't add too much. Should be enough. Now we haven't talked about the formula of hydrogen peroxide in here yet. The formula for hydrogen peroxide is H2O2. It's H2O2. And that's not one of the, peroxides aren't one of the things that we learned when we went through nomenclature. So if you don't get that, that's all right. So I'm going to pour this into the Coke bottle. And then I'm going to place it into this, I guess it doesn't fit, huh? Alright, well we'll just leave it like that. And then I'm going to take some manganese 4 oxide. Manganese 4 oxide. And I'm going to add the manganese 4 oxide to the bottle, but before I do I need you to close your eyes. Make a wish. All right, you can open them up. Dump this in. And your wish is granted. Now, unfortunately, this one is not getting as hot as I had hoped it would get. Dump a little more in. There we go. Shoot. Wow, that is hot. There we go. And what I had hoped actually would have happened, darn it. What I would have hoped had happened, and it didn't quite go far enough. Sometimes we can get this to heat up enough, and probably because it tipped over we didn't get it, but it should have fallen down into the beaker. Let's try it again. I brought one more just in case because, I don't know, I think they've changed the size of these things. I used to use 24-ounce bottles and I put them in a 400 ml beaker and it just was snug. And these here now are just, it's a little bit too big for a 250. But we'll try it again here. But I'll try to hold on to it this time. See if we can't get it to work. All right. And I think I was shorted it on the hydrogen peroxide, so we'll put a little extra in this time. There we go. What will probably happen is I'll wind up with some nice hydrogen peroxide burns on my hand later. And I always thought it was good. I'm not teaching lab this semester, but whenever I found student papers that looked like this, that was always a good sign. That means that your papers were in the lab, right? Okay. If I come and I see these lab reports that come with all these nice clean sheets, it was always suspicious. All right, so we'll try it again here. You don't need to make a wish this time unless you want another one, granted. We'll dump it in. Again, I think this probably isn't going to work. How disappointing is that? Well, that's all right. Just, again, probably because I'm dealing with 20-ounce bottles that they sell here rather than the 24-ounce like they used to sell, which fit a lot snugger than the other ones. Is it going? Is it going? Not quite. All right. Anyhow, had it shrunk down and gotten hot enough, I don't know if any of you have ever seen these before, but these here are, you can pass these around. These are, all right, thank you. These here that I'm passing out, these are molds that are used to make like 2-liter bottles and pop bottles like this. And what they do basically is they inject them down into a mold and then they blow steam into them to expand them. And if we get these hot enough, which this is kind of beginning to show, but we didn't get it quite hot enough on this one here, is that if we get it hot enough, this would actually fall down into the beaker. And I'm not getting it quite hot enough here today to do that. But if we wanted to write out a chemical equation for this reaction, we could do that. And here's how we would first of all go through the description. It's like this. We'd say that hydrogen peroxide and this is an aqueous solution of hydrogen peroxide, sorry. An aqueous solution of hydrogen peroxide decomposes in the presence of a manganese 4 oxide catalyst to yield water and oxygen gas. So it yields liquid water and oxygen gas. I'm going to wipe this up so it doesn't leave stains. So now if we want to show this in terms of a chemical equation, we'd start first of all by writing the formula for hydrogen peroxide. The formula for hydrogen peroxide again is H2O2. Phase label is going to be aqueous. This is an aqueous solution. And now, if we want to put in a catalyst, anybody know what a catalyst does? Speeds up a reaction. Exactly. And that speeds up a reaction without being consumed. So a catalyst speeds up a chemical reaction without being consumed. Which means, of course, if I had dumped in 2 grams of manganese 4 oxide at the beginning, how many grams should be in here right now? 2 grams. It should be exactly the same at the end as what I started with. And in a chemical equation, we write the catalyst above the arrow. So again, this is written above the arrow in the chemical equation. It's neither reactant nor the product. So now we need the correct formula for manganese 4 oxide. A Roman numeral of 4 means that we have Mn with a charge of 4 plus. Oxygen here is O with a charge of 2 minus. O with a charge of 2 minus, and I'm looking in the wrong class. How did I get the wrong class here? I've been taking notes in the wrong class the whole time. How about that? Alright, so where am I? Right here. O with a charge of 2 minus. So the formula for manganese 4 oxide is Mn O2. And that's because we need 2 of these oxide ions to balance the charge of every one of the manganese. Formula for water would be H2O, and the phase label, liquid, and then oxygen gas would be O2, the phase label, G. So now at this point we'll go ahead and balance this chemical equation. Now as we look at this, the simplest formula is O2. So we'll balance the oxygen last. Means we balance the hydrogen first. So the balance of hydrogen, how many hydrogens on the left? 2. How many hydrogens on the right? 2. Let's balance. That means we go back to the oxygen. How many oxygens here on the left? How many on the right? 3. So now, we did say we want to leave this one to last because it means we should be able to put some coefficient here in front of the O2 to balance it. We just don't know what that is. The problem is, if you start thinking of using whole numbers now, like a 2 or 3 or whatever, then that makes the side even bigger. So this takes us to strategy number 3. And strategy number 3 says, if necessary, use fractions to balance the number of atoms on each side of the equation and multiply through to remove all fractions from the final answer. So coming back to this one here, there's a couple ways we can go about doing this. One way is to do this algebraically. So if we look at this, how many oxygens are there here again? There's 2. And we know that the two sides must be equal, so how many do we have here? There's 1 here. And right here now we have some number times 2. And in algebra, if you wanted to show some number, you would label it with an x. So we'd say x times 2 or 2 times x. So this now is your algebraic equation that shows what we need to do. We then subtract 1 from each side. Once we subtract 1 from each side, we find out that this is a 1 over here, and this is we subtract the 1, so that's a 0 now at this point. So we now have 2x is equal to 1. To solve for x, we then divide each side by 2. We find out that x is equal to 1/2. And so put in the 1/2. Now you might have been able to reason this a different way. If you're already looking at this and you say there's already too many oxygens on here, on the right hand side, we only wanted 2 on each side, then right away you'd say, well, I need to put in some sort of fraction there, and you probably should have been able to guess a fraction of 1/2 is right. Because of course 1/2 times 2 is 1, and 1 plus 1 gives us 2, which matches on each side. We can't leave the fraction in here, so we then take the entire equation and multiply it by a factor of 2. Once we multiply the entire equation by 2, we distribute that 2 throughout. It gives us a 2 here, a 2 here, and coefficient of 1 for the O2. And this is your balanced chemical equation. Now you should always verify when you go through a series of steps that it is still correct once we've distributed it through. How many hydrogens here on the left? 4. On the right? 4. Oxygens on the left? 4. Here we have 2 plus 2 gives us 4. This equation is balanced. Now this particular one can get these two rules, or these two strategies we should say, can often be used interchangeably. If we want to show how this even-odd one works, we can come back to this equation and say, well, let's use this even-odd strategy. Remember that when we look at this, you're going to leave oxygen to last. Of course, when we look at hydrogen, say, oh, well, it's already balanced, so we come back to the oxygen. We now think of only using whole numbers. Let's start putting numbers like 1, 2, 3, and 4, whatever in here. No matter what coefficient we put in front of here, the number of oxygens is always going to be what type of number? We put in a 3, the number of oxygens on this side is going to be even. We put in a 4, it's going to be even. 5 is going to be even. Any number times an even number is always going to give you an even number. So then when we look at this side, we see the number of oxygens is an odd number. So we have to somehow make the number of oxygens on this side an even number, because we can only have even numbers here on the left. So if we want to make an even number on this side, what kinds of coefficients do we need to put in front of which substance? We need to put what type of coefficients in front of this one here? Even. Because the number of oxygens in this formula is an odd number. And if it's an odd number, we know we can only have even numbers over here, and that means we have to multiply this by an even number. We just don't know which even number yet, so the best strategy is always to start with the smallest even number and work up to larger even numbers. So the smallest even number that we could use is 2. If you put that in, then we have 4 hydrogens and we have 4 oxygens. Conveniently enough, then we can put a 2 over here to give us the 4 hydrogens and 4 oxygens on the left. So again, there's multiple ways to do these. Just think about the different strategies that you may use. Now, if you had balanced it and come up, now this is a balanced chemical equation. You could have come up with 6, 6, and 3. If you went through, you would have seen that this is a balanced chemical equation. But mastering chemistry will always assume, as will always chemists assume, that they're always reduced to the lowest whole number values. So each of these coefficients can be reduced by a factor of 3. And so if you can ever reduce your coefficients down, you reduce them down. In this case, then we reduce them down to 2, 2, and 1. And again, that is the convention that mastering chemistry will use, the back of the book will use. The convention I will use is always to have them reduce to the lowest whole number values. Any questions on these? Any questions? All right, next up. We're going to look next at completing and balancing chemical equations. Completing and balancing chemical equations. I'm going to go to the right class this time. So when complete and balanced chemical equations, that means you're going to be given the reactants, and you need to figure out what the products are. So again, we're going to work on completing and balancing chemical equations. And there's going to be 2 different types of chemical equations that you will need to complete and balance. They are combustion reactions and double displacement reactions. In double displacement, often called double replacement reactions. They're the same things. I think if you go into lab, we call them double replacement reactions in lab. So these are the 2 types you are responsible for completing and balancing. There's other types, but you're not going to be responsible for completing those equations. So we'll start first of all with this one here. We'll say if a reactant contains let's say it contains the element carbon. And we'll also look at hydrogen. And we'll look at sulfur. And now we're looking at these now are combustion reactions that we're looking at. So let me zoom out here. We're going to start with combustion reactions. So maybe we should kind of step backwards here a bit. If we say that we combust something, what does that mean? If something is combustible, what does that mean? Anybody know what combustion is? Not pressure. Burning. It's burning. If something goes through combustion, that means we burn it. And most of us here today got here using an internal combustion engine. It's called an internal combustion engine because inside your engine you are doing what to your gas? Burning it. Right, you're burning it up. This here that I'm doing with this burner, this is combustion, and we burn stuff. Okay, so if a reactant contains carbon, when you burn something containing carbon, carbon is converted into what stuff? What do you think? Well, think about it now. Carbon is going to react with oxygen to make carbon dioxide. So something that contains carbon gets converted to carbon dioxide. If it contains hydrogen, the hydrogen is going to get converted to H2O. Yeah, converted to H2O. Now we don't use sulfur a whole lot. We haven't at this point. But if it contains sulfur, it gets converted to sulfur dioxide. And sulfur dioxide would be SO2. Alright, so if a reactant contains carbon, it gets converted to CO2. If it contains hydrogen, it gets converted to H2O. If it contains sulfur, it gets converted to SO2. So let's go back to this very simple one that we have right here. And we want to write out a reaction for what we're just observing. We want to write a reaction for what's happening right here. Now the stuff that comes in here is piped in, contains a substance called methane. This is a substance called methane. Actually, it's a little bit more than methane. There's some ethane in there as well, but about 70% of natural gas, 70-80% of natural gas is methane. And by the way, methane is colorless and odorless. And you probably, some of you know, methane is, many of you are accused of producing methane, right? Because if you poot, fart, whatever, many will say that you're producing methane. Actually, they're lying. There's only about a third of us that are methane producers, okay? But if you've ever seen the thing where they light farts and stuff, you know, not everybody can do that, okay? Not everybody can do it. There's only about a third of you are methane producers. If you went behind a cow, you could, because cows are methane producers, but humans, only about a third of us are, okay? So, if they're accusing you of producing methane, they don't know what they're talking about because methane is colorless and odorless. So, we come in here then and say, well, he just told us colorless and odorless. You go down here and smell this stuff, it smells really bad. Why does this stuff smell so bad? Well, it's not mixed with oxygen. Why do you think we'd want to add something to this? So we can smell leaks, exactly. So I don't know if any of you come down Connie Road 7 into Anoka every day. If you come down Connie Road 7 up around 160 some street there, there's an odorant facility on Connie Road 7 on the way up to St. Francis. And they add in an odorant, and it's a sulfur-containing compound that's added in, and that's just so we can tell that there is a leak. They add in just a small amount. It's called a mercaptan, and mercaptans are actually similar to chemicals found in skunk. And as you know, you could have a skunk get hit, and it could be a mile away. You can wind up smelling it because these mercaptans have very, very, very strong odors, and that's the type of compound that's added into natural gas to help us smell it. All right, so lesson learned. If somebody accuses you of producing methane, they don't know what they're talking about. Only a third of you do. All right, so, not that I've sampled you guys, all right? So now, we want to write out a reaction for this. Methane has a formula of CH4. And if we burn something, what is it reacting with? O2, good. Whenever you burn something, remember we're reacting with oxygen and We now want to figure out what the products are. So carbon would get converted into carbon dioxide. Hydrogen would get converted into H2O. So again, carbon gets converted into CO2, oxygen or hydrogen gets converted into H2O. Now if we want to put phase labels in for all of these, the natural gas coming in here is a gas. Oxygen, of course, is a gas. The carbon dioxide produced is a gas, and the water that's produced here is a liquid. I don't see any liquid there. It's produced as a gas, right? So now, if you want to go ahead and balance this chemical equation, go ahead and do it, please. All right, coefficients. Help me out here. Left to right, they would be 1, 2, 1, and 2. Any questions on this one? Okay, next one. Most of you here today got here by driving or riding with someone. I know some of you might ride a bike. Primary component of gasoline. Anybody know the primary component of gasoline? You go to the gas pump. It talks about certain types of ratings. There's a number on there. Octane ratings, exactly. Octane has a formula of C8, H18. C8, H18 is the formula for octane. So now, write out a chemical equation that shows the complete combustion of octane. Write out a chemical equation that shows the complete combustion of octane, which again is C8, H18. So again, remember what it means. If you combust something, that means you're burning in the presence of oxygen.